second subtopic, which is on induced EMF. Okay, so in this subtopic, you should be able to explain induced EMF by using Faraday's experiment, state and use Faraday's law, state and use Lenz's law to determine the direction of induced current, derive and use induced EMF in a straight conductor coil rotating coil. Okay, so induced EMF. Faraday's law of electromagnetic induction states that the magnitude of induced EMF is proportional to the rate of change of magnetic flux. Okay, so mathematically it can be written as the one shown here. Okay, so d phi here is the change of magnetic flux, whereas dt is the change of time lah. Okay, so the negative sign indicates, oh okay, where is my negative sign? Okay, I forgot to add the negative sign, but I'll add them before I'll upload in GC lah. Okay, so this one is negative dv over dt. Okay, so there's negative sign there. So the negative sign is just the direction of induced EMF lah. So it is indicating that the direction of EMF is always opposing the change of magnetic flux producing it. Okay, so that's when we go into Lenz's law lah. Okay, so for a coil of n turns, so if there's a number of turns of coil, we can then just multiply it with the number of turns n lah. Okay, and since the change of magnetic flux is this equation here, it can also be written as the one shown here lah. Okay, so my final minus initial lah. Okay, and if the coil of n turns is placed in a changing magnetic field, the induced EMF is given by this equation here. Okay, so what is changing? The magnetic flux is the one that is changing, which is this one. Okay, but if the coil's area is the one changing, the induced EMF is then calculated using this equation lah. Apa yang different is only this rate of change. This is rate of change of magnetic flux density, and this is rate of change of coil's area. Okay, okay, so for a coil connected in series to a resistor of resistance R and the induced EMF exists in the coil as shown here, the induced current is given by this equation here. Okay, so we know that induced EMF is equal to negative n and the rate of change of magnetic flux, and we know that also EMF is equal to IR. So combine these two equations, hence we get this this equation lah, where I is actually rearrange it for I, kamu dapat lah induced current. Okay, so note that the negative sign is in all this equation can be ignored when you are calculating the magnitude of induced EMF. Okay, so you don't have to include the negative sign because it's just telling us the direction is always opposing the change of magnetic flux lah. Okay, so for a coil of n turns, each turn will have a magnetic flux of BA cos theta through it. Okay, so the magnetic flux linkage is given by this equation lah. Ini bila ada magnetic flux linkage lah. Okay, so this is important as well lah. Alright, I think that's all for our second subtopic. Oh, sorry, there's more. Okay. Alright, now let's go on to Lenz's law. Lenz's law states that an induced electric current always flows in such a direction that opposes the change producing it. Okay, so it always opposes the change producing the induced current. Okay, so this is a form of law of conservation of energy lah. And some of these can be explained through experiments. So let's look at our first experiment. So the magnitude of the magnetic field at the solenoid will increase as a bar magnet moves towards it. Okay, so this bar magnet is moving towards this solenoid here. So it causes the magnitude of the magnetic field to be increasing. Okay, so because of that motion, an EMF is induced in the solenoid here, okay? So when there's an induced EMF, there will be an induced current. So that's why the galvanometer is showing us that there is a current flowing through this wire, okay? But we do not know the direction of the current, hence we can use the right hand grip rule, okay? So we can use right hand grip rule just to determine the direction of the induced current, okay? So the induced current flows in such a direction that as to produce a north pole approaching, okay? So it is, the induced current will move in a direction that produce a north pole at the solenoid here, okay? So why does it do that? Is because it is trying to oppose the approaching magnet, because the magnet here is a north pole, and this induced current tries to produce a north pole here so that it goes away lah, so it is unapproachable, so that it is trying to oppose this magnet from coming towards it, okay? So this opposes the motion of the bar magnet, hence telling us that it obeys the Lenz's law lah, okay? So it obeys Lenz's law, okay? Yeah, okay, so that is on our first experiment, and then let's look at the second experiment. So for the second experiment, what he used a straight conductor, okay? Instead of a solenoid, now he uses a straight conductor PQ, okay? So it is placed perpendicularly to the magnetic field and move the conductor to the left, okay? So it is moving to the left with constant velocity. So when the conductor is moving to the left, the induced current needs to flow in such a way that it opposes the change, okay? It doesn't want it to move, so it's trying to oppose the change based on Lenz's law lah. Hence the galvanometer here is showing a deflection lah. Okay, now again, how to determine the direction of the induced current and also the induced EMF? We are gonna use the Fleming's right hand rule, okay? So now we are using Fleming's right hand rule, okay? So the thumb is showing us the direction of motion, our pointing finger is showing us the direction of magnetic field, and the second finger, which is our middle finger, telling us the direction of the induced current ataupun the induced EMF, okay? So the induced current will flow from Q to P. So since the induced current flows in the conductor PQ, this conductor will experience a magnetic force. Remember, if there is movement in the conductor and it is placed in a magnetic field, the conductor will experience a magnetic force lah. So the magnetic force will be in the opposite direction of the motion, okay? Okay, now the third experiment pula. So there's two solenoids P and Q arranged coaxially close to each other. So at the moment when the switch is closed, current will begins to flow in solenoid P and producing a magnetic field, okay? So there's magnetic field in solenoid P, okay? So suppose that the field point towards solenoid Q, so it goes dia terkena dengan solenoid Q, the magnetic flux through solenoid Q will increase with time lah. And then according to Faraday's law, we know that an induced current due to induced EMF will exist in solenoid Q, okay? So the induced current flows in solenoid Q will then produce a magnetic field, okay? So the magnetic field that being produced will oppose the change producing it, causing an increase in flux lah. Okay, so in the induced current flows in circuit consists of solenoid Q here will be anti-clockwise, and the galvanometer will show a deflection, okay? And then when the switch is open means that they off the switch, the current will then starts to decrease in solenoid P, and magnetic flux through the solenoid Q here will also decrease with time, okay? So according to Faraday's law pula, an induced current due to induced EMF will still exist in solenoid Q sini, okay? So the solenoid the induced current flows in solenoid coil will then produce a magnetic field that oppose the change producing it. So there's a decrease in flux below. The switch is already turned off here, and then based on Lenz's law again, the induced current flow in circuit will then be clockwise, and the galvanometer will be deflecting to the opposite direction. Okay, so what you need to know here is that Lenz's law is always try to oppose the change that's producing it lah. Okay, and then the direction ni kamu perlu tahu macam mana mo how to find the direction lah. Okay. Oh, this is a very long subtopic. Okay, now induce EMF in a straight conductor pula. Let's consider a straight conductor PQ of length L. So this is length L. Move perpendicular with velocity V across a uniform magnetic field. Okay, so it is moving to the right, perpendicular to the magnetic field. So when the conductor moves through a distance of x, which is this one, the area swept out by the conductor is given by a Lx. Okay, so since the motion of the conductor is perpendicular to the magnetic field, hence the magnetic flux cutting by the conductor is given by this one here. Okay, how do we obtain that? Is theta is equal to 0, so that gives us 1, and we know that the area is L times x, so we have obtained magnetic flux density equal to BLX. Okay, so according to Faraday's laws, the induced EMF is given by this equation here lah. Okay, so in general, the magnitude of induced EMF is given by ELVB sine theta, where the angle theta is between V and B. Okay, between V and B. Okay, so this type of induced EMF is known as motional induced EMF because the straight conductor moves, then there's an induced EMF. That's why it is known as motional induced EMF lah. Okay, so the direction of the induced current or induced EMF can be determined by using the Fleming's right hand rule lah. Okay, it is based on Lenz's law, which is this one lah, Fleming's right hand rule. Okay, now in the case of figure 4, the direction of the induced current ataupun induced EMF is from Q to P lah. Kamu determine that by using Fleming's right hand rule. Okay, so the at point P will have a much higher potential than Q lah. Okay, so note that the equation here can also be used for a single turn of rectangular coil lah. Tapi kalau dia ada bagi number of turns, just multiply it with n lah. Okay. Now, I think this is the last one for this subtopic. Yes. Okay, so last one, induced EMF in a rotating coil pula. Tadi in a straight conductor, now rotating coil. Okay, so let's consider rectangular coil of n turns, each of area A being rotated mechanically. Okay, so it is rotated mechanically with angular velocity of omega in a uniform magnetic field of flux density B. Okay, so when the vector area A is at an angle theta, which is this one, the magnetic flux through each turn can be calculated by using this equation here. Okay, but let's apply the Faraday's law for a coil of n turns. Hence, we can then calculate the induced EMF to be this one here. Okay, so this one is for magnetic flux, this one is for induced EMF. Okay, now the induced EMF will be at a maximum. Okay, will be at a maximum when sine omega t here is equal to 1. Hence, we can then obtain EMF NBA omega. This is at a maximum. Okay, kalau soalan tanya calculate the maximum induced EMF, kamu just directly use this equation. Okay, where omega is equal to 2 pi f and 2 pi over t. Okay, now this is the induced EMF punya equation, where the theta here is the angle between the vector area and magnetic flux density, sorry. Okay, actually I'm just if you want to remember this, write it, actually write it this way. And actually cantik pula, tapi at least you remember lah dia punya angle tu apa. Okay, so theta is the angle between these two here. Okay, kamu ingat je lah kalau macam tu. Alright, so as a conclusion, a coil rotating with constant angular velocity will produce a sinusoidally alternating EMF, as shown in the graph here. Okay, so it's rotating this way, so it will produce a sinusoidal punya EMF lah. Okay, alright, so that is our subtopic 5.2, which is on induced EMF.